Hello, everyone. My name is Xiaozhu Meng from Rice University. Today, I'm going to present our paper, Parallel Binary Code Analysis. This work is collaborated with the University of Wisconsin-Madison. Binary code analysis has significant application to multiple domains, including performance tuning, security analysis, debugging, reverse engineering, and software forensics. Increasingly, we have seen multi-gigabyte binaries generated by compiling sophisticated applications and framework. Traditionally, binary analysis is single-threaded and is too slow for large binaries. Let's consider a typical performance tuning example. An application developer starts with an application source code, compiles the source code to binary code. The developer then profiles the application to get performance measurement and also uses binary analysis to recover program structure. Performance measurement and program structure are then combined to do performance attribution. Finally, the developer uses performance metrics to optimize the source code. This tuning cycle is repeated until the developers are satisfied with the software performance. Now let's focus on the binary analysis step. It is beneficial to construct control flow graphs from the binary to report performance at the loop-less level. And the binary analysis must be repeated after any source code is changed. That is because even small code changes can lead to very different binaries. In our experience, serial binary analysis is too slow and can take over 80% of the total program structure recovery time and leads to over 20 minutes spent in the binary analysis step. This slows down the performance tuning cycle. Note that this observation holds even for non-running iterative scientific computations, as they can be tuned based on the analysis of measurement of a few iterations. To address the speed requirement, we aim to perform parallel CFG construction. Since binary code is naturally split into binary functions, we explore function-level parallelism. However, there are several challenges to resolve. First, binary functions may share code, so different threads analyzing different functions still require careful synchronization. Second, as existing serial algorithms for CFG construction do not explicitly identify data or analysis dependencies, it is not obvious how to reason where synchronization is necessary. Third, doing our work, we actually find that serial algorithms may generate different results if the functions in the binary are analyzed in different orders. And some orders may yield wrong results. Therefore, we cannot just simply parallelize existing algorithms. We also need to refine the algorithms to produce consistent results. To systematically address these challenges, we present a CFG construction abstraction. It includes defining primitive CFG construction operations, including creating blocks, edges, and functions, determining block address ranges. These primitive operations are trivial to perform in serial, thus existing serial algorithms do not explicitly define them. Defining primitive operations allow us to treat CFG construction as a sequence of CFG operations applied to an input graph. A typical input graph is just a set of function entry points extracted from the symbol table. As shown in the diagram, we have an input graph on the left, and then we apply a block creation operation and several edge creation operations. And key advantage of such abstraction is that then the correctness and performance property of CFG construction can be reasoned by considering the relationship between individual operations. We consider operation dependencies, which would specify the required order of applying operations. An example is applicability dependency, which means that one operation becomes possible only after another operation is applied. For example, we can only create an ongoing edge of a block after we have created this block. We also derive operation commutativity. Intuitively, commutative operations can be reordered. As shown in the diagram, we have two block creation operations to perform, creating a block along edge X and creating a block along edge Y. These two operations can be performed in either order, and we will get the same result. In this paper, we also introduce other types of commutativity, but the key takeaway here is that with commutativity, we understand the flexibility we have to allow threads to perform concurrent operations in arbitrary order, and the order won't impact the final results. Now, before diving into the details of our new approach, let's first review how CFG construction is done in serial. A common approach is called a control flow traversal. It starts with no function entry, such as A and B shown in the diagram, and then follow the control flow transfer to identify more code and new functions. The focus of control flow traversal is to analyze several challenging code constructs generated by the compiler. Next, we will discuss three challenging code constructs, describe how serial algorithms handle them, and what additional challenges they bring in the context of parallel CFG construction. The first challenging code construct is function sharing code. Functions may share code that has common functionality, such as code for error handling and stack frame setup and teardown. Binary analysis tools often represent a multi-entry function as multiple single-entry functions, and these single-entry functions naturally share code. To correctly represent shared code, a function is often defined as the set of basic blocks reached through only intra-procedural edges from the function entry. Functions sharing code is a fundamental challenge for parallel CFG construction because threads analyzing different thread functions must synchronize when analyzing shared code. While function sharing code is rare in source code, it is not uncommon in binary code. We have seen sharing as high as 70% in a system library on Linux. The second one is non-returning functions. Binary analysis tools often create call fall-through summary edges to represent that a function call will return to its call site. As shown in the diagram on the left, the red edge represents that the call instruction will transfer the control flow to function B, and eventually the control flow will come back to the call site. Call fall-through edges are created to avoid analyze function call target when traversing the CFG of the caller. However, function calls may not return as shown in the diagram on the right. Function B will terminate the program execution, thus function call to B inside A will not return to this call site. It is important to not create call fall-through edges in such cases, as wrong edges will lead to confusing control flow. Existing non-returning function analysis performs name matching for no non-returning functions such as exit, defers call fall-through edge creation until knowing the call limit return. And if a function does not reach a return instruction, then it must be non-returning. In the context of parallel CFG construction, the analysis of non-returning functions causes analysis dependency, as the analysis of caller depends on the analysis of callee, which may eventually cause analysis serialization. The third one is tail call, which is an optimization that uses a branch instruction to perform a function call. A tail call is only possible for function calls at the end of a function. Tail calls means that not every branch instruction should be labeled as intra-procedural. Tail call identification is based on heuristics. For example, a branch to a known function entry point is a tail call, and a branch that has stack frame teardown before it is a tail call. However, different analysis order may generate different results. Consider the example shown in the diagram where we have function A and function B. A includes a call instruction to address 0x40, and B includes a branch instruction to the same address. Now let's examine the function boundary of B in two cases. In the first case, we first analyze function A and then B. We will find that address 0x40 is a function entry because it is a target of a call instruction. When we proceed to analyze B, we will find that the branch instruction's target is a no function entry. Therefore, the branch is a tail call, and 0x40 is not part of the function B. Case 2, if we analyze B first and then A, branch in function B will not be identified as a tail call because 0x40 is not a no function entry, nor it contains stack frame taildown. Therefore, 0x40 is part of B. We can see that the function boundary in B is different when the analysis order is different. We design a new parallel CFG control flow construction algorithm to not only speed up CFG construction, but also generate consistent results. Our new algorithm has 3 features. First, it supports efficient concurrent CFG operations. Second, it carefully orders CFG operations for better performance. As we discussed, commutative operation can be applied in any order. We will also try to address the analysis dependencies caused by non-returning functions. Third, our algorithm will produce consistent results for tail quantification. The consistent results are achieved by doing CFG construction in 2 phases. The first phase is parallel control flow traversal to add graph elements. The second phase is parallel control flow finalization to correct the wrong results. Let's first look at the first phase, parallel control flow traversal. The algorithm takes Q as input, and Q is a set of function entry points extracted from the symbol table or frame information. We sort functions in decreasing sizes to heuristically balance the workload among threads, as large functions tend to require more time to analyze. The main component of the algorithm is the async finish model for task parallelism. The async clause creates new tasks, and the finish clause synchronizes tasks. Each task analyzes one function and launches new tasks to analyze newly discovered functions. This model of task parallelism avoids the need of a global task queue. Then let's look at the delay func data structure, which is used to handle non-returning functions. Delayed func records unresolved caller-to-callee non-returning dependency. Process a func will add entries to it when analyzing call side, and remove entries from it when reaching return instructions or when a function has been determined to be non-returning. After the finish code block, all functions in delayed func that forms a cycle are non-returning. This is because that at this point, all tasks have finished, and we have not found any return instructions in this function yet. These functions cannot return and will be analyzed in the next iteration of the algorithm. Next, let's discuss how threads concurrently build a graph. While analyzed functions, threads are synchronized based on 5 invariants. We will discuss the first 4 using an example. In the following several slides, we'll use an example to discuss the 4 invariants we designed. Each slide will contain a diagram split into the top half and the bottom half. The top half represents the state before applying certain operations following an invariant, and the bottom half represents the results. At the beginning, we have 5 threads, T1 to T5, following 5 different edges to a shared region of code. The edges here are just for illustration purpose. The first invariant is about creating basic blocks. There is at most 1 basic block starting at any given address. Following this invariant, T1, T2, T4 create blocks. T3 and T5 leave the code region as there is already a block created at their target. The results are shown in the bottom half. At this point, we create 3 blocks, B1, B2, and B3, but we do not know where these blocks end yet. To implement this invariant, we use a block store map that is implemented with a concurrent hash map in TBB. which synchronize threads branching to the same target and also allowing threads branching to different target to proceed independently. The next invariant is on block ending. There is at most one basic block ending at any given address. Now let's say T2 reaches the block end while T1 and T4 are still in progress as shown in the bottom half. Following the invariant, T2 registered block end. This invariant can be implemented with a block end map using concurrent hash map from TVB. You may see that T1, T2, and T4 have performed redundant analysis on a subset of address range. For example, T1, T2, and T4 all have decoded machine instructions shown in the green region, which is a waste of work. An alternative implementation is to look up block store address after decoding each instruction to detect block ending. This alternative can avoid redundant instruction decoding, but will create a hotspot of the block store data structure. So here we prefer to perform potential redundant instruction decoding to reduce the block store map lookup. As instruction decoding is thread safe and has no synchronization, it will not cause scalability issue. Next, we discuss invariant edge creation. The thread that registers block end is responsible for creating outgoing control flow edges from that block. In this example, as T2 has registered block end, T2 will be responsible for to create outgoing edges and then leave the code region. To ensure that only T2 creates the edges, we put the block and registration and edge creation in one critical region. Therefore, after T1 reaches the block end, T1 has to wait for T2 to finish creating edges. A key advantage of this design is that no redundant edges will be created. Finally, we need to split blocks, as basic blocks typically do not overlap. So in this case, T1 has reached the block end and realized that someone else has registered block end. So T1 knows that another block, which is T2, ends at the same address. Based on the block splitting invariant, T1 proceeds to split the block. As B1 originally contained B2, we adjust B1's block end to be the start of B2's B2 and add a fall through edge from B1 to B2. While T1 is splitting the block, T4 waits for T1. Then T4 proceeds to split the block. As B2 contains B3, we need to adjust B2's end and create an edge from B2 to B3. In contrast to the first case of block split, note that B2 used to have 3 outgoing edges. As B2's end address has been changed, these outgoing edges do not belong to B2 anymore. So T4 also needs to move edges from B2 to B3. Now, all threads have finished the work on this code region. Next, let's look at the new queue, which represents the new task item to launch. New queue may include newly discovered functions when encountering call instructions, may include func, the current function to analyze, and the callers of func. Note that we may put the current function back to the new queue to reduce serialization caused by non-returning function dependencies. Let me explain this in more detail now. Recall that to correctly determine whether we should create a call fall through edge of the call site, we need to know whether the callee is non-returning or not. Long call chains may cause analysis serialization, as shown in the first diagram. A calls B, and the analysis of A cannot continue until we know B returns or not. However, B calls C, and the analysis of B cannot continue until we know C returns or not. We know that we cannot resolve this issue in general, but we have a strategy that works well in practice. In practice, most functions return and have multiple return instructions. As shown in the second diagram, B can reach a return instruction in a separate path, Once the analysis of B discovered a return instruction, we terminate the analysis of B immediately and put A and B into the new queue. Our algorithm will then immediately launch new tasks to analyze both A and B. This can minimize the chance of analysis serialization. Finally, we briefly talk about control flow finalization. Control flow finalization determines function boundaries, which can be done with a concurrent graph traversal from function entries going through only intra-procedural edges. Control flow finalization also fixes inconsistent telco results. Here is the telco example we showed before, where depending on the analysis order, function B may or may not contain address 0x40. The key insight here is that doing control flow finalization or control flow graph elements have been found. So we have more information to make a consistent decision. Specifically, 0x40 is a definitive function entry as we must have analyzed the call instruction in A. Therefore, we can mark the branch instruction in B as a tail call. Now let's look at some results. We implemented our parallel CFG construction algorithm in Dynast and verified the correctness of our implementation by comparing our results with the ground truth derived from Dwarf debugging information. We will then focus on discussing the performance aspects of our results. We measured the performance using HPC struct from the HPC toolkit. HPC struct recovers program structure from binary code for performance attribution. It uses Dynast for binary analysis. HPC struct includes CFG construction, parallel code for dwarf parsing, and some serial code for printing structural information to files. We use 4 large binaries for evaluation. These 4 binaries are from real-world applications, which ranges from a few hundred megabytes to about 8 gigabytes in terms of size, and includes x86-64, big endian power, and little endian power in terms of architectures. Let's first look at results without parallel CFG construction. The prior column lists the running time in seconds of HPC struct with serial CFG construction. So HPC struct had a speedup of 2x to 5x with 16 hardware threads. Using more than 16 hardware threads hardly improved performance. The percent SCFG column lists the running time percentage of serial CFG construction. It shows that serial CFG construction is clearly a bottleneck, taking about 40 to 80% of total runtime when HPC struct runs in parallel. In summary, serial CFG construction significantly limits the parallelization of HPC struct. Now let's look at results with parallel CFG construction. The current column lists the running time in seconds of HPC struct with parallel CFG construction. It shows an end-to-end speedup of 6x to 8x, which is much higher compared to HPC struct with serial CFG construction. The CFG column lists the running time in seconds of parallel CFG construction. We achieve a speedup of 9x to 12x for parallel constructing CFGs with 16 hardware threads and up to 25x with 64 hardware threads, showing that our parallel CFG construction scales well. HPC struct is now limited by other serial phases, and the total running time of HPC struct has been significantly reduced. In summary, we find that an abstraction of CFG construction is the foundation for efficient parallel algorithm for CFG construction. Parallel CFG construction significantly accelerate code analysis tools that require CFG. In the future, we plan to develop parallel implementations for other types of binary analysis techniques, including data flow analysis and binary instrumentation. And this is end my talk. Thanks for watching the video.